Hello, thank you. I'd like to talk about the Dezign-8 puzzle. This is one of Kadon Enterprises puzzles and some things I found out about it. So it was created by Bill Biggs in 1959. It has 64 tiles representing various ways a path can emerge from 1, 2, 3, or 4 sides of a square. There's a photo of the actual puzzle. Now, for the purposes of describing the tiles, I gave arbitrary names to the 8 different types of tile. You'll notice that all of these are mirror symmetric except for the 2 on the right, which are mirrors of each other. And I give the distribution because it turns out the distribution is going to be important in what follows. So an interesting property you note about these tiles is every time you put them together to make a solution, the number of loops in the solution is equal to the number of connected components. So this, on the one side, I illustrate one big connected component. In fact, there's one loop or hole. On the right-hand side, there are 2 because of the circle in the middle. We consider that 2 holes, and there's certainly 2 connected components. I also, just to hammer the point and to save slides, I've thrown in the axes of symmetry, and I'll be talking a little bit more about symmetrical solutions a little later. Okay, there are 2 ways you can make a sort of maximally symmetric solution. I had always been working with orthogonal symmetry because it has the advantage you take 1/4 of the tiles, you solve that, and then the other 3/4 of the puzzle are solved for you. But it's not the only form of a symmetric solution. You can also have a solution that's symmetric along the diagonals. In fact, I haven't completely finished sort of analyzing solutions that are symmetric in this way. For example, I know what the maximal number of components is for orthogonal symmetry. I don't know what the maximum number achievable is for diagonal symmetry. Okay, this loops equals components has to do with those counts we had. It's not a property of that set of those kinds of tiles. It's how many we chose of each one. So obviously, sort of here are 2 extremes. If we chose different tiles from that set, in one case we'd have 32 components and no loops. In the other case, we'd have 1 component and 49 loops. So the question is, what is special about the distribution that was chosen for this set? So we go back, as some of the other talks have, to Euler's formula. Everyone's sort of familiar with vertices minus edges plus faces. For a disconnected graph, we can throw in components. And the observation is that if I have 2 connected components, I can draw an edge from one of the subgraphs to the other one of the subgraphs. The number of components goes down, the number of edges goes up, and so edges can be traded off for components. So using this formula and rearranging, obviously, it shows if the vertices equals the edges and the faces equals the components, which is what we're trying to show. So we need a graph somewhere around here. So I introduced some vertices onto the tiles. In fact, not all of the tiles. Now I will consider each of those blue dots as obviously one vertex, but I'm going to consider a line from a vertex to the edge of a tile to be half an edge, because obviously you need 2 of them to go from vertex to vertex. So a solution then gets an associated graph. Now you may complain that I haven't done anything with the square in the center, but the sort of corner pieces or the diagonals that can form closed loops kind of don't count in what we're trying to set out to prove here, because we want to show that loops equals connected components, and a closed path like that adds 1 loop and 1 connected component, so it evens out. So I could actually have a more complicated ordering where I added more dots so that everything showed up, but it wouldn't change the end result, and so I stayed with the simpler set. So summing up the table with the frequencies we have there, my table shows that the number of vertices is the number of t pieces plus the number of plus pieces plus the number of n pieces, etc. And for our particular distribution of tiles, we get vertices are 36 and edges are 36. So here's a maximally symmetric solution with 19 components, which is the max, discovered by Daniel Austin in 2005. But it irked me that we couldn't, that I haven't shown you 13 yet, and that we don't have rotational symmetry. So by tweaking the tile set in ways that if I can talk, it's described more in my paper, I tweaked the set of tiles, and here's my 13 components, 13 loops, and full dihedral symmetry with a modified tile set. Thank you. And thank you, Kate Jones.